I'm going to talk about inverses of functions. All right? Let me start with an example. Suppose we had the function f of x equal to x plus 1 and the function g of x equal to x minus 1. Now let me create a table of corresponding values with respect to each function. After I do that, you will notice an interesting pattern. So for the function f, I'm going to create a column in the table that holds some x values. And to the right of each of those x values, I'm going to put the corresponding function values. For example, f of minus 1 is 0, so I'm going to put a 0 next to the minus 1. F of 0 is 1, so I'm going to put a 1 next to the 0. And likewise for the other x values. Okay? And let me do likewise for the function g. All right, so let me pick some x values. And then let me write the corresponding function values next to each of those numbers. So g of 0 is minus 1, so I'm going to put a minus 1 next to the 0. G of 1 is 0, so I'm going to put a 0 next to the 1, and then likewise for the other numbers. Okay, so here's the interesting thing. Notice that if you swap the column of numbers for each table, you get a table that looks like the other one. Okay? So, for example, the column, the first column, the left column of the left table has what values? Minus 1, 0, 1, 2, 3. Notice that that's the same column that's in the notice that's the same set of values as the left column of the left table. Okay, likewise, the column of function values for the left table is equal to the column of x values for the right table. You can, of course, extend these tables with other x values, with other corresponding function values, and you would notice that this pattern, this property still holds. Okay? When two functions are said to be inverses of each other, this pattern will hold. Okay? Now, a related pattern appears with respect to compositions of these two functions. For example, let's calculate f of g of 0. So to do that, we would first calculate g of 0, which would give us minus 1. And so now we would calculate f of minus 1. And f of minus 1 would give us 0. All right? Now, so the thing to notice is that we started with 0 and we ended with 0. Okay? That's going to happen with all the values of all the possible x values when two functions are inverses of each other. Let's try another example. G of f of 3. So f of 3 is equal to 4. So now let's find g of 4. G of 4 is equal to 3. All right? Try to find the corresponding composition values for several x values, and you'll see that the value that you start with is the input value is the same as the output value. Okay? So whether you describe inverses in terms of tables or compositions, both of those are valid ways to think about what inverse functions are. Let me now state the definition of inverse functions with respect to compositions. if functions f of x and g of x are inverses of each other, then f of g of x equals x and g of f of x equals x for their domains. So for all x values in the corresponding domains, that must be true. Okay? So we can use this definition to determine if an arbitrary pair of functions are invertible, are inverses of each other. So for example, suppose we had the functions a of x equal to 2x plus 1 and b of x equal to x minus 1 over 2. And we wanted to determine if they were inverses. Let's find the composition a of b of x. Okay, so that gives what? We have to determine an expression equal to a of x minus 1 over 2, and that would give us 2 times x minus 1 over 2 plus 1, or x minus 1 plus 1, which is equal to x. All right, let's try b of a of x. So that's equal to b of 2x plus 1, which is equal to 2x plus 1 minus 1 over 2, or 2x over 2, or x. So both compositions are equivalent to x, and so therefore we know that these two functions are inverses of each other. Okay? Now let me show you a procedure to find inverses of functions. Okay? I'm going to state the description of the procedure with a cutesy little sentence so that it's easy to remember, and then I'll show you an example to show you what I mean. Okay? So to find the inverse of a function, do the following. Swap x and y and solve for y. All right, so what do I mean by that? Let's go back to the two functions we were just working with. All right, so we had a of x equal to 2x plus 1 and b of x equal to x minus 1 over 2. And let's assume that we didn't know that the inverse of 2x plus 1 was equal to x minus 1 all over 2. Okay, in that case, you could find the inverse of the function a as follows. So first, denote the function a by the variable y. Okay, now swap x and y. So in other words, every occurrence of y, replace it with x. Every occurrence of x, replace it with y. So that would give us x equals 2y plus 1. Now we solve for y by subtracting 1 from both sides and dividing by 2 now. Okay, and lo and behold, we got the correct inverse function. Okay? Now, if you understood that, I want you to try to find the inverse of a function now. Try to find the inverse of m of x equal to 1/3 x plus 1. Pause the video and try that now, please. Okay, I'll go ahead and show you how I would do it. So I'm going to work with the equation y is equal to 1/3 x plus 1. Then I'm going to swap the x and y as before. Now I'm going to subtract 1 from both sides. And then I'm going to triple both sides. So there you have it. That's the inverse. Okay? 3 times the binomial x minus 1. Now, I'm going to erase the board in a second, and I'd like you to do one more. So would you please find the inverse of n of x equal to 2 minus x? So pause the video and do that now, please. Okay, I'll go ahead and work that out. So y is equal to 2 minus x, so x is equal to 2 minus y. How about adding y and subtracting x from both sides? So that gives y is equal to 2 minus, y is equal to 2 minus x. Now, notice something interesting about the inverse function that we found. It's equal to the original function. Okay? It's possible for a function to be its own inverse. All right? So keep that in mind. Now that I've given you a procedure to find the inverses of functions, let me immediately say that not all functions have inverses. All right? Watch what happens if we try to apply the procedure I just showed you to a function that does not have an inverse. Suppose we had the function q of x equal to the absolute value of x. So trying to find its inverse, we would work with the equation y equals the absolute value of x, and then x equals the absolute value of y. And how do you solve that equation for y? How do you isolate y? Okay, so the best we could do is determine that y is either equal to x or minus x. Okay, but we can't quite finish solving for y. We don't know which expression is equal to y. See the problem? Here's another example with a similar problem. R of x is equal to x squared. So we would work with the equation y is equal to x squared, and then x is equal to y squared. And then what would happen if we tried to solve that? Well, we can't solve for y. The best we could do is determine that y is equal to the square root of x or minus the square root of x. All right? Now, when functions do not have inverses, you can still find inverses for limited domains, for restricted domains. Let me repeat that. When a function does not have an inverse, you can still find an inverse of sorts if you're willing to settle for a smaller domain. So, for example, for the function q, if we limited ourselves to x values greater than or equal to 0, then the inverse function would be x. Likewise, for the function r, if we limited ourselves to x values greater than or equal to 0, then we could find an inverse function. The inverse function would be the square root of x. Okay? Let me close by talking about the graphs of functions and their inverse. You're going to notice an interesting property that's going to be very useful. So let me first draw an xy coordinate plane, and then we'll continue. Now, the first thing I want to do is I want to draw the line that corresponds to the equation y equal to x. Okay? Now, I'd like to make a claim. If you graphed any function and its inverse, you would notice that both graphs are reflections of each other. Let me repeat that. The graph of a function and the graph of its inverse are always reflections of each other. They are reflections of each other with respect to the line that corresponds to y equal to x. Okay? For example, we just saw that the x squared function had an inverse equal to the square root of x for the limited domain with respect to positive x values. Let's plot the x squared function with respect to positive x values. So that would look something like the following blue line. Okay, now let's plot its inverse. So the inverse would be the square root of x. Okay, and let's plot that with the plot will look something like the following purple line. All right, so you see how those are reflections of each other with respect to that green line? Okay, now the reason that this property is holding is because this is related to that initial observation with respect to swapping the columns of numbers. Okay, think about that and you'll understand why this property has to hold. Now, this property is actually going to be used to create a method to help you determine if a function has an inverse or not. All right? In order to understand this method, you need to know what the vertical line test is. If you don't know what the vertical line test is, I would invite you to watch my video on that topic. Okay? A function, a graph can only be the graph of a function if it passes the vertical line test. Okay? Now, likewise, a graph can only be the graph of the inverse of a function if it passes the vertical line test. Right? Okay, here's the punchline. The only way that the reflection of a graph with respect to y equals x, the only way that the reflection is going to pass the vertical line test is if the original function passes what's called the horizontal line test. Okay? Let me type what I just said so that everybody's clear. Horizontal line test. If it is impossible to draw a horizontal line that intersects the graph of a function at more than one point, then that function is invertible. So you want to see if you could make a horizontal line that touches the graph in more than one place. So if you look at the blue line, think about several horizontal line segments. None of them touch the blue line in more than one place. So that's why the graph of x squared with respect to positive x values is invertible. Okay? Another name for functions that are invertible is one-to-one. They're one-to-one functions. Okay? Now, I'd like to show you the graphs. I'd like to show you several graphs, and we'll close with this. I want you to determine for each graph if the function is invertible or not, if the corresponding function is invertible or not. If it is invertible, I'd like you to sketch the graph of the inverse function, the corresponding inverse function. All right, so let me sketch several graphs. So remember, after I draw these graphs, you're going to want to determine which ones are not invertible. If they're not invertible, maybe put an X next to those graphs, and then the ones that are invertible, go ahead and sketch the graph of the inverse. All right. Okay, so there's one example, another example. All right, pause the video and determine which of those are invertible, and then determine the, or not invertible, and determine the graphs of the ones that are invertible. Okay, so pause the video and do that now, please. Okay, I'll go ahead and show you how I would determine, how I would do this exercise. So I'm going to draw horizontal lines through graphs that don't correspond to invertible functions. Okay, so for the remaining functions, I'll draw a sketch of their reflections with respect to y equal to x. Okay, something like that.